So welcome. Hi, I'm recording that. Okay, so welcome everyone to this week's Sydney CPPC seminar. So today's speaker is Giorgio Busoni, who is currently a research fellow at the ANU. And so he obtained his PhD from CISA in 2015 and then came to Australia, to Melbourne, for his first postdoc. And then he moved on to Heidelberg, to the Max Planck Institute in Heidelberg. And now since this year, since beginning of this year, he's a research fellow at ANU. So Giorgio has been working on dark matter and made many contributions. In particular, he looked at a validity of effective field theory at colliders. And now more recently, he moved into basically looking at astrophysical objects and specifically at capture of dark matter in compact stars and what we can learn about dark matter from this. And today he will be telling us about his research on exactly that topic, on capture of dark matter in compact stars.
Thank you for the nice introduction. So yes, I will present you our results that we got in this series of papers on capture of dark matter in compact stars. This was done together with my collaborators, Nicole Bell, Sandra Lobers, and Michael Brigato. So I will start by trying to tell you why we should look for dark matter signatures in compact stars and why to calculate dark matter capture rates in this kind of stars. I will then try to review the main differences in between the capture in the sun and the capture in neutron stars, and we'll again go to the results. So I guess you are all familiar with direct detection. In direct detection, we have two main kind of interactions, the spin-independent ones and spin-dependent ones. Now, for the spin-independent ones, we are able to get stronger constraints because they are coherent in between the various nucleons inside the nuclei, and so you can get stronger constraints. However, in the detection, we have some dependence on the kind of targets that we choose. Moreover, these two kind of interactions are not the only one that one can have in nature, because there are, if one writes a full list of effective field theory operators, one can see that there are several interactions that are called momentum suppressed or velocity suppressed. And that means that they have, due to the kinematics of direct detection that happens at in a non-relativistic regime, these operators would yield a small cross-section that is suppressed by powers of the momentum transfer or by the velocity. On top of that, in the detection, we have the problem that the experimental detectors have energy thresholds. So some kind of a signature might be unable to be seen. So for example, you lose sensitivity for small dark matter masses because the energy, recoil energy is small, or there are some other kind of signatures, like if you have some if elastic scattering is not possible, because, for example, you have inelastic dark matter where you have two states, and dark matter can only upscatter inelastic to the heavier state, and you have some mass splitting in between the states, then the scattering might be kinematically forbidden, or anyway, due to the fact that you have a mass gap, the final recoil energy might be too small to be seen. Now, an alternative way to look for dark matter that is probing the same parameter space is dark matter capture in stars. Now, dark matter can be captured and accumulated in stars. So you can think of stars moving around the center of the galaxy as hit by a wind of dark matter particles. And this wind of dark matter particles, sometimes some particles can scatter on some nuclei inside the star. And if in the scattering they lose enough energy, they can become gravitationally bound, and then they would be forced to stay inside the star and undergo some more scatterings, and finally ending up in this accumulating in the center of the star. Now, if dark matter can annihilate, the final states would in general be trapped inside the sun, but neutrinos would be able to escape, and we can observe neutrino on Earth. So this is a way to set limits using dark matter capture in the sun. Now, for spin-independent interactions, usually direct detection provides stronger constraints. But in the case of spin-dependent interactions, usually the sun gives stronger constraints. Now, of course, this kind of this is model dependent because you have somehow to choose an annihilation channel for your dark matter particles. And depending on the channel, you can get different quantities of neutrinos and a different spectrum. Another way to infer indirectly the presence of dark matter in the sun is, for example, to look at modified energy transport inside the sun. So if dark matter has a mass that is in between 1 and 10 GeV, approximately, one can it cannot annihilate. It can accumulate inside the sun and it can contribute to energy transport. And this is something that was analyzed, for example, in these papers here. Now, why looking at neutron stars? Neutron stars, first of all, are very dense objects, and this means that they are very efficient for capture. Now, given their density and their size, one can see that one can potentially capture the whole dark matter flux that is incident on the star, already for cross-sections that are as small as 10 to the negative 45 centimeters square. That is in the ballpark of the best direct detection limits for spin-independent interactions. So what are the possible observational signatures? So first possibility is that by accumulating dark matter, the mass of the star is increasing enough to cause the collapse to a black hole. But this is unlikely to happen for fermionic dark matter, and it's more likely to happen for bosonic dark matter. Another possibility is to look for signatures in gravitational waves of black hole mergers. But what we will concentrate on is are the last two bullet points, that is kinetic heating and kinetic plus annihilation heating. So looking at the evolution of the temperature of the neutron star, and the neutron stars have no known large heating sources. That means that we think they should lose energy indefinitely, and the temperature should go down indefinitely. Now, the two main mechanisms are by neutrino and photon emission. Neutrino emission dominates the early stages of the life of the neutron star, and the photon the late stages. Now, in the absence of other heating sources, one expects the temperatures of about 1000 Kelvin after 10 megayears, and 100 Kelvin after 1 gigayear. However, if the neutron star can interact with dark matter with a cross section that is of the order of 10 to the negative 45 centimeters square, what happens is that for each scattering event of a dark matter particle with the neutron star, some heat would be deposited inside the neutron star. And this is a kind of heating mechanism. And in the presence of this heating mechanism, the temperature would not go down indefinitely, but would go to an equilibrium temperature that is about 1700 Kelvin if the whole dark matter flux can be captured. On top of that, if dark matter after being captured can annihilate in the center, then additional energy would be released inside the star, and the equilibrium temperature can be raised to something of the order of 2400 Kelvin. Now, to estimate this heating rate, what we need is the capture rate, whose maximum value is the geometric one. And then we need the average energy release for each dark matter particle that's captured. That is of the same order of the dark matter mass, due to the fact that the dark matter is accelerated to relativistic speeds by the gravitational field of the star. So once we calculate our capture rates, we can define a threshold cross-section in this way, that our capture rate is equal to the geometric one times the ratio of the cross-section to the threshold cross-section. And in this way, we can find that the equilibrium temperature for a certain capture rate is equal to the maximum one, the temperatures quoted in the previous slide, times the ratio of the cross-sections to the 1/4. Now, what are the advantages of the neutron star? First of all, we have a large probability of capture. This is due to the fact that it's very dense. And it's also thanks to the fact that the dark matter is accelerated to relativistic speeds. And these relativistic speeds also mean that any momentum or velocity suppression of some operator is washed away. There is another advantage that, as we saw, that we are sensitive to cross sections of the order of 10 to the negative 45 centimeters square and below. There is no threshold requiring energy, unlikely as in the detection. The various interactions are all similar sensitivities, both spin dependent and spin independent. And so based on what we said in the previous slide, if one is able to observe a neutron star whose temperature is below the equilibrium temperatures quoted before, then one can effectively say that the cross-sectional interaction with dark matter has to be smaller than the threshold cross-section times the ratio of the temperatures to the fourth. Let me show you a couple of examples where this is quite powerful. So our first example is inelastic dark matter. As we said, in the case of the Earth, it's quite difficult to probe this kind of inelastic dark matter where you have two states and elastic scattering is not allowed. Now we can see that in the case of a neutron star, we can reach mass splittings of the order of 300 MeV. While instead on Earth, what you can achieve is something like 3-4 orders of magnitude less. So I think the kinematic threshold is something like mass splitting of the order of 100 keV on Earth. But on top of that, you have to add that you need to have enough recoil energy to be able to see the event in the detector. And so that means that it's unlikely that you are able to observe anything that has a mass splitting above something like 30 keV. So that makes up the 4 orders of magnitude. A second example are the momentum suppressed operators. So here on the right, you can see the limits that you can get on the coefficients of these effective field theory operators for 3 different temperatures of the neutron star that you can observe. So even taking the most conservative one of 1700 Kelvin, we can see that we get similar constraints for all the operators, while on the same plots, you can also see direct detection constraints. And you can see that these are better than the neutron star only in the case of operators D1 and D5 that correspond to the spin independent ones. But in all the other cases, the direct detection constraints are much weaker. And in some cases, you cannot even see them on the plot, like for the operator D4. Now, what are the detection prospects for this kind of cold neutron star? So we hope that we will be able to see some of these stars using the James Webb Telescope that was launched on Christmas Day last year. This is a nice NASA infographic about the telescope. And this is a comparison with the Hubble. The main difference with Hubble is that Hubble is principally operating in the visible spectrum, while the James Webb Telescope will operate mostly in the infrared. That is exactly the kind of wavelength that we need to observe this kind of star. Now, here are some rough estimates for the detection of this kind of star. Now, these cold neutron stars are very faint objects, so they need a large observation time. So here on the right, I show you the maximum distance that one can probe as a function of the temperature for a certain time. Now 10 to the 5 seconds correspond roughly to 1 day. So these observation times are quite large, but 10 to the 6 is something that is for sure achievable, realistic. And in the second plot, I show based on the expected number density of neutron star in our surroundings, how many neutron stars one can hope to be able to observe for a certain, as a function of the temperature. Now, as you can see, even with the observation time of 10 to the 6 seconds, we hope that we will be able to observe a few neutron stars that are in between 2000 and 1000 Kelvin, let's say. To be able to observe a colder neutron stars, one would need definitely a larger observation time. assuming that the estimate for the number density is correct. At the moment, the coldest neutron star that we have observed has an upper bound on the temperature of 42,000 Kelvin. So now let me come to our work. So we started from the formalism for dark matter capture rate in the sun that was developed by Gould in the 80s. And we tried to adapt this formalism to neutron stars. To do that, we have to perform a large number of updates in the calculation. And I will try to review them all in the following slides. So we start from the treatment of gravity. So in the case of the sun, stellar models give us a density profile that we can use to solve the Poisson equation and find the gravitational potential. And this will be the information we will need to calculate the trajectories of dark matter inside the star. In the case of neutron stars, one needs to choose an equation of state. And these are not known, but there are several possible options that one can choose from. And once you do that, you need to solve the relativistic version of your Poisson equation that are the 12 equations. And by solving the 12 equations, you find the value of the metric inside the star. Now, once you do that, you can find your expression for the capture rate in terms of your interaction rate omega. And as you can see, for the sun and for the neutron star, these expressions are pretty similar. There are two main differences. The first one is that in the case of the neutron star, there is a separation of scales in the speeds, because the speed of the dark matter in the halo, so at an infinite distance from the star u, is much smaller than the escape speed, that in the case of a neutron star is the speed of light in practice. That allows you to perform analytically the integral over the initial speed distribution that is not possible to do in the case of the sun. The second difference is this factor B at the denominator in the case of the neutron star, that is a kind of gravitational redshift. Now, going to the kinematics, your interaction rate in the case of the sun is usually written in this form, where V is the final speed of the dark matter particle, S is the speed of the center of mass, and T is the speed of the dark matter particle in the center of mass. Now, what is usually done in the case of the sun, that one considers the targets at rest, and this is the origin of these delta functions. If one doesn't want to do that, one will, instead of the delta functions, will have some integral over the initial state distribution that is the Maxwell-Boltzmann. And one also have a lower bound on the final speed V that is a kinematic bound. Now, in the case of the neutron star, we have a similar expression where this time S and T are the Mandelstam variables, because we wanted to rewrite this using some relativistic invariance. And on top of integrating over the initial speed distribution, initial energy distribution, that is this n, that this time is a Fermi-Dirac distribution, we also have an additional factor that is 1 over n, that is in fact the final field distribution, because we needed our final state to go to a state that is not already occupied due to the Fermi-Dirac statistics. So we will see that this will cause a Pauli blocking effect that is important for low dark matter masses. Another important thing is that in the case of the neutron star, one in fact does not have a lower bound on the momentum transfer as long as the dark matter mass is below 10 to the 6 GeV. And this is once again because of the separation of the scales of the two speeds. Now, going to the dynamics, in the case of the sun, usually the differential cross-section is expanded in terms of the powers of the relative speed and the momentum transfer. And the most common choice is to choose n and m equal to 0, so that means a constant differential cross-section times a form factor that depends on the target. Now, in the case of the neutron star, instead, we need to consider the full dependence on the two Mandelstam variables S and T. And so we rewrite this expression in terms of the relativistic invariant matrix element M, and you can plug as M any matrix element you want of your favorite dark matter model. We chose to operate with an effective field theory, so we have plugged in the matrix elements of this full set of dimension 6 operators, but you can use the matrix element of the interaction you like more. On top of that, we still have a form factor that we will see that we will need to include in the case of hadrons, because hadrons are composite particles, and we will see that we will be able, with the momentum transfer of that we have in the Neutron Star, we will probe the internal structure of hadrons. So going to the stellar model, as anticipated in the case of the sun, we have we know with very good precision the physics of the sun inside. So we have we know to very good precision all the profiles of temperature, density, abundances of the various elements, pressure, and the gravitational potential. In the case of the Neutron stars, the equation of state is not really known. So we have chosen two different benchmarks, that is the BSK24 and the QMC. And for each of these benchmarks, we have chosen 4 different masses of neutron stars that are allowed by this equation of state. And you can see the principal values of these benchmark points that we get once we solve the equation of state to get the various profiles. And this is for QNC. Now, QNC turns out to be more suitable for heavier stars, and we will see that it will let us account for the hadron interactions inside the neutron star, and this will lead to an important effect. And here I'm showing you some of the profiles you get once you solve your equation of state for these particular benchmark points. Well, one thing to note is that in the case of QNC, if the star is enough heavy, some exotic baryons can appear in the core of the star, as you can see on the bottom plot. Now, in the case of the neutron star, we have to deal with the degenerate matter, and that has 2 main consequences. First one is that targets have cannot be considered to be at rest, but they have a Fermi momentum. And this will affect the maximum value of the momentum transfer for any target. This will be particularly important for light targets and light dark matter. So when the dark matter mass is smaller than the chemical potential. And here on the bottom, you can see the maximum value of the energy transfer as a function of the dark matter mass for a fixed value of the chemical potential and different values of the parameter B in the metric. As you can see, for large dark matter mass, this tends to be a constant, so to constant values, independent of the mass, of the order of a few GeV. And on the right, instead, we fix the mass of the dark matter to be heavy, and we see how this maximum energy transfer depends on the chemical potential and on the value of the metric B. The second important effect is that, as anticipated, the target needs to scatter above the Fermi surface. So this leads to a Pauli blocking effect that is important for light dark matter. So in these plots, I will try to quantify the effect of the Pauli blocking. Here we showed the differential interaction rate of dark matter as a function of the energy transfer with and without Pauli blocking for 3 different choices of dark matter mass on the 3 columns and 2 different choices of the chemical potential for the upper row and the lower row. So starting from the top left, we can see that for 1 GeV dark matter and chemical potential of 100 MeV, only the part of the potential that has an energy transfer below the 100 MeV is affected. And if you calculate the total interaction rate, that is the integral of these 2 curves, the difference is mild. However, if you start to decrease the dark matter mass, you see that the effect starts to become very large. In fact, you can see that in the central plot and in the plot on the right, the scale is now logarithmic scale. Okay, so there is a very large suppression due to Pauli blocking, and the interaction rates get suppressed by orders of magnitude. By going on the bottom row, you can see that if you increase the chemical potential to 400 MeV, already at 1 GeV, you get a significant suppression of the total interaction rate. That means that Pauli blocking will be stronger for larger values of the chemical potential, and the chemical potential is larger towards the core, towards the center of the star. So you expect for low dark matter mass that capture will happen more closer to the surface, so in the more in the outer layers. And this can be seen in these plots, where we plot the differential capture rate as a function of the distance from the center, by including or not including the Pauli blocking effect. And as you can see, for MK of 100 MeV, the effect is very large, and the peak of the differential capture rate is moved to the outer layer of the star. Now, in the plots of the right, you see the same quantity for MK equal 1 GeV and 10 GeV. And as you can see, for a dark matter mass of 10 GeV, the effect is not there. And for 1 GeV, the effect is an order 1 effect, but it's still moving the peak of the capture rate towards the outer layers of the star. Now, going to the form factors, in the case of the Sun, the form factors of the various nuclei usually have this form of an exponential function times a polynomial function. And the variable of this function is ER over E0, where ER is the recoil energy, and E0 is an energy scale that is of the order of few MeV, and becomes smaller for heavier targets. Instead, the recoil energy grows with the mass of the target. So you can see that the two, the E0 can be equal to the maximum recoil energy already for targets that are as light as 14 GeV. So it's important to you include the form factors in your calculation in the case of the Sun. When it comes to Neutron Star, we are pretty much in the same situation. This time, the form of the form factor is different. But once again, the scale that enters the form factor is this Q0 that is of the order of 1 GeV. And as we have seen before, the energy transfer, but also the momentum transfer is of the orders of several GeVs. So this will lead to important consequences. On top of that, as anticipated, we should account for the fact that there are strong interactions and a strong mean field, inside the Neutron Star. So this mean field will play a role similar to the Higgs field, and will change the mass of the neutrons. Will give an effective mass to neutrons and protons that is going to be smaller than the rest mass, and it will depend on the distance from the center. So here you can see in these plots that for the heaviest Neutron star we consider, this effective mass can be as low as the half of its rest mass. Finally, we will consider how to deal with the multiple scattering in this kind of stars. Now, in the case of the Sun, as we said, the speed of the matter at infinity u is of the same order of the escape speed. This means that usually to account for the effects of multiple scattering, you need a simulation. Now, in the case of the Neutron Star, instead, we have a separation of scale. And we can see that thanks to that, we are able to treat multiple scattering analytically. Now, the energy that dark matter needs to lose to get captured is the energy test at infinity. So it's 1/2 MK U squared. That is of the order of 10 to the negative 6 MK. Instead, the energy transfer in a single scattering, as we saw, is of the order of a few GeV. So one needs a number of scatterings that is the range of these two quantities. So it's of the order of 10 to the negative 6 MK over GeV. And from now on, we will call Mstar the dark matter mass for which you need on average one scattering to get captured. Now, if you look at the variation of your momenta, of the dark matter momenta, delta P over P, you see that for each scattering, this has a value that is about Q0 over MK. And so it's much smaller than 1 for large dark matter masses. However, if the dark matter mass is so large that it doesn't get captured in a single scattering, you need to find the total delta P over P, you need to multiply this by the number of scatterings. If you do that, you find a quantity that is independent of the dark matter mass and is of the order of 10 to the negative 6. This means that the fraction of momenta lost is a small fraction. The moment variation is a small fraction of the total momenta. And because of that, you can assume that along all the scatterings, the trajectory of the dark matter particle is not altered. And this will simplify a lot comparing to the sun, where this is not true, because after each scattering, you can have a small but non-negligible scattering angle. And when you sum up all scatterings, this can become large. Now, to calculate multimode scattering probabilities, the basic ingredient will be our probability density function of energy loss. That is practice the normalized differential interaction rate. Starting from this, you can calculate the probability Pn to lose an energy of delta, to lose an energy delta after n scatterings. And you can do this for any n. And after that, you can find the probability of getting captured after n scatterings using this equation 24. Now, as you can see, in this case, to calculate this probability, you have to integrate over the initial speed distribution. So in this case, the integral over the initial speed distribution will kick back in your expression for the capture rate, and you will not be able to perform this analytically anymore. Now, luckily, whatever is your probability, density probability, you find out that the function Pn of delta quickly tends to a theta function. And this simplifies a lot the computation for large n. Here you can find on the bottom the first 5 probability functions as a function of delta for heavy dark matter mass. And on the right, you can find the probabilities that you get by integrating over the initial speed distribution in the case of the Maxwell-Boltzmann. Now, as you can see, they follow a simple scaling law, and we find out that we can fit these probabilities with this fitting function that only requires a single parameter, that is once again Mstar. So to calculate Mstar, first of all, we need to find to good accuracy our density probability density that are obtained by calculating the differential interaction rates. And to do that, we find the analytic expression for the various interaction rates of the interaction we want to consider. By doing that, we can find the exact values of these Mstars. And these values will differ between the various interactions by order of 1 factors. But in any case, the scale, the order of magnitude of Mstar is always set by the reasoning of the previous slide. So by this separation of scales. One important thing that you need to account for is the form factor. So, in our first work, we were not including the form factor, and the interaction rates were the one in light blue, while by including the form factors, we get the interaction rates in purple. So as you can see, the interaction rates are shifted towards smaller energies. And smaller energy transfers means that you will need more scatterings to capture your dark matter, and will mean smaller values of Mstar. Now, once you have calculated your probability to get captured after an interaction Pn, you can put this together with the probability to interact at least n times. That is a function of the optical depth tau. And you can formally solve the problem by making resumming this infinite series. And this would bring the capture rate equation in this form, where you have an integral over the initial speed distribution and volume. And you have this kind of convolution function, G, that is basically what you get by summing up equation 30. That depends both on the optical depth and the energy loss. However, this is not really a practical solution, because you would need to sum. I mean, if you cannot perform the sum explicitly, you will need to truncate it to some large value of n. And this large value of n would grow with the linear with the dark matter mass. That means if you want to compute the dark matter capture rate for a dark matter mass that is 10 times larger, you would need to sum over 10 times more values of n. And the computation time would scale linearly, therefore, with the dark matter mass. So instead of doing this, instead of requiring n scatterings to have a dark matter capture, we take a probabilistic approach, and we assign a probability 1 over n of dark matter to get captured after each scattering. And we can see that in this case, we can solve the problem exactly. Now I will skip the math in these slides. Basically, all you need to input is this coefficient A in equation 39, that is the survival probability after the scattering. So if the dark matter mass is below 10 to the 6 GeV, we saw that the probability of capture is 1, and so A is 0. So what you get after that is that you should input in your capture integral this factor eta, that is nothing but this exponential of minus tau, the optical depth. So you can interpret this in the sense that this factor avoids you to double count the interactions. So our integral, what really gives our integral gives is the number of interactions as a function of the flux of dark matter particles that is hitting the star. And you want to, in practice, once the dark matter particle is captured, we want to remove it from the flux. You don't want to continue to use the flux that you have on the surface. So this factor accounts for that. If the dark matter mass instead is above 10 to the 6 GeV, the survival probability is now 1 minus 1 over n star, when this n star is the same as n scattering that we had in the previous slides. This is the way we call it in the paper. And so it's basically 1 minus m star over m cap. And by doing the same maths as before, you get a different factor eta, that is this one, 1 over n star times an exponential of minus tau over n star. So once again, you can find the physical interpretation for this. So our equation, our equation really gives is the interaction rate, the total interaction rate in the star. And if each scattering corresponds a capture event, this is equal to the capture rate. But if you need n scatterings to capture the matter, then the capture rate is you need to divide the interaction rate by n. So that's the factor 1 over n. And the exponential factor has exactly the same meaning as before. Just this time, you want to remove the particle, the matter particle from the flux after n scatterings instead of 1. And that's why you divide the tau by n star. So what we did is taking our different operators, we calculated these values of m star. And here on the left, we did that by neglecting the interactions. And but by considering and not considering the form factor. So the ones with the form factor are the solid lines, and without the form factor are the dashed lines. So as expected, you can see that the values of m star become smaller once you consider the form factor. After that, we turned on the interactions, and we calculated how these values of m star change by changing the target mass, so by using the effective mass. Once again, you can see that this effect can become quite important, especially when the target mass becomes particularly smaller than the rest mass. So putting all of this together, we can go to the results. Now, first warning, we start from leptons. In the case of leptons, leptons are very light. And because of that, in neutron stars, they are very degenerate, and they have a very low mass. And they are very relativistic due to the low mass. So because of that, the relativistic treatment is very important. So here on the right, you can see a plot taken from this paper where they were computing the bounds coming from neutron stars using electron targets, using the two different approaches, relativistic and non-relativistic. And as you can see, the relativistic approach is completely wrong because it's overestimating the bounds at small dark matter mass by orders of magnitude, and it's underestimating it at large dark matter mass by orders of magnitude. So that said, these are our results for the capture rates for electrons and muons inside the neutron star. And by using this, we can obtain these plots here, these exclusion plots here of sigma versus m chi, where we compare the limits that we could get from neutron stars with the current limits coming from direct detection. So as you can see, the limits from neutron stars would be much more powerful than any limit coming from direct detection, both current and future experiments. On the bottom, we do the same thing in the case of the white dwarfs. And also here we can see that the limits one could potentially get are pretty strong. In all the cases, one would potentially be able to go below the neutrino floor that is shown in yellow. Going to baryons. So in this first plot, what we want to show is the importance of considering both the interactions and the form factor. So here we show the capture rates that are calculated by considering or not considering both of these two effects. And so we have 4 possible combinations. The case where we don't consider any of them is the dashed blue one that is used as a reference. And the case where we consider both of them is the purple solid line. And on the bottom of the plots, we plot the ratio of each case to the reference case that is the dashed blue line. So as you can see, by including these effects, unfortunately, our capture rates become smaller, and that will mean that we will be able to have constraints that are weaker, unfortunately. We can see that these effects can be particularly important for certain operators at large dark matter masses, for example, D4, where they can reach 3 orders of magnitude. And they are also very important at low mass for the protons. And that's because basically, in the case of the protons, if you don't consider the self-interactions of the medium, you are neglecting the polyblocking effect. So these plots refer to a neutron star of 1.5 solar masses. If we go to 1.9 solar masses, we not only we have neutrons and protons, but we also have these exotic targets. And here we plot the capture rates of the various components of the various targets, and the total capture rate in as a dashed blue line. That is, again is set as a reference. And on the bottom, you see the ratios, so the fractions, the contribution of each target. As you can see, these exotic targets can be a quite important contribution in certain cases, and can be even the dominant contribution, like for the operator D4 at the large dark matter mass. Now, in these plots, we can see how the threshold cross-section is going to change by including the two effects, so the interaction and the form factor. As we can see, as expected, the threshold cross-section will become larger, so that means weaker limits. And this is particularly important at large mass for neutrons, where we can get an effect of more than an order of magnitude. And in the case of protons, also at low dark matter mass, due to the fact that one neglects polyblocking in the other case. Finally, these are our plots for possible exclusion bounds using neutron star versus their detection. The top plot refers to spin-independent interactions, And as you can see in this case, the detection has a stronger constraints in the range of masses where it's known to perform very well. That is between 10 GeV and several 10 or 100 TeV. But in the rest of the mass spectrum, Neutron Star potentially perform better. And in the lower two plots, we have instead the spin-dependent interactions for protons and neutrons. And in this case, neutron stars outperform any current and future detection experiments, and they're even able to go well below the neutrino floor. So coming to the conclusions, I hope that I've shown you that neutron stars are a nice cosmic laboratory to probe dark matter interactions. They have a completely different kinematic regime comparing to the detection experiments. They have the feature that the high energy scattering is washing out any momentum suppression and any other kind of kinematic suppression that you can have, like with the inelastic scattering. We are able to probe a very large mass range of dark matter particles, and they are very sensitive to all kinds of interactions, including the so-called momentum suppressed ones, and also with the lepton targets. Now, at the moment, as I anticipated, the coolest neutron star that was observed has a temperature of the order of 10 to the 4 Kelvin. But hopefully, there are good prospects for observation in the coming decade for a neutron star that is enough cold to be able to use this mechanism to constrain dark matter interactions. I hope you have enjoyed the talk, and if there are any questions, they are welcome.
Yeah, thank you very much, Giorgio, for a very interesting talk. So we have time for questions. Who would like to go first? Maybe I start to kick us off. So can you go back to slide 60?
Yes.
Yeah. So for your lines here for the constraints from neutron stars, what are the assumptions in there? So what is basically, so these are current bounds or future ones?
No, once again, for these bounds to be able to be placed, you need to observe a neutron star that is a temperature below those values that decided at the beginning. So below 1700 Kelvin, let's say.
Okay.
If you're ever able to observe one of them, you can automatically set this exclusion bound. And if you are able to observe some neutron stars that are even colder than that, yes, these bounds get pushed even further down.
Thanks. Can I follow up on one thing? So yeah, where do the 1700 Kelvin come from? So they basically, you said basically it comes from that dark matter capture. So if the whole flux is captured,
yes,
does it depend in any way on the dark matter mass or?
No, so I can go back to the beginning. So you get basically that, what is it? So as you can see, the maximum capture rate is the geometric one, and is inversely proportional. It's proportional to 1 over m chi, but then the energy transfer is proportional to m chi. So it does. So if you take the product, that is the heating rate, it's independent of the dark matter mass.
But it assumes that your dark matter follows some Maxwell-Boltzmann distribution, and
you need to assume. You need to assume. In this case, this formula is for a Maxwell-Boltzmann, but you can assume any speed distribution. It has to be anyway something that has the speeds below the escape speed from the galaxy, right? So it's going to be something similar. You will get a different over factor. Not this F function, but for any physical speed distribution, you will get something that is of this order of magnitude.
Okay, good. Thanks. Other questions?
Yeah, can I ask maybe a very naive question, Giorgio? So these neutron stars with the captured dark matter, if I understand correctly, they also affect the equation of states in neutron stars, right? Yes.
So we don't really consider that. because the amount of dark matter that is captured is anyway a small fraction compared to the total mass. Yeah, so we don't really include the option for.
I see. So that's irrelevant for your case. Is that correct?
Not sure if it's relevant or not. Maybe not an expert in this field. Many.
But how about for light dark matter? Because you said that Pauli blocking, Pauli blocking played a role. So the Fermi-Dirac distribution, you really fill the whole Fermi sphere with it. So you have a large number of.
Yeah, you would expect that you would soften a little bit, you know, that maybe, I don't know, qualitatively, but you would expect to soften the equation of state. And that could be, in principle, if it happens, I don't know, if then it could be interesting to look also the neutron star binaries and then extract that information from gravitational waves through the tide of the permeability.
Yes, I think this is what I was inputting here at the second bullet point, that you can, there are people that have looked into this, I think.
Okay. I see. Okay.
Other questions? I have another one. So you mentioned a form factor dependence. So how well are those form factors known? So if you basically you had initially no form factor included and then later you included one, but do we know those form factors well enough, or is there more uncertainty in there?
So this is probably more a question for Tony Thomas, because I had the intuition that there could be an import a form factor effect, but we were asking him about what is the right form factors to be used.
Yeah, certainly for the neutron and proton, the vector form factors are pretty well known. The axial vectors, not bad. Some of the other form factors, scalar form factors, would be less well known. But you're talking about order of magnitude effects rather on the capture cross sections, as opposed to you know, 10 or 20% uncertainties in form factors. There's no ambiguity really in the size of the effects.
Okay. Thanks. Do we have more questions? Can you go back to that slide 64? So at the end, there was, so they discussed those effects. So there are two main effects, right? Are that Pauli blocking and multi-scattering. Is that right? Which
so we have Pauli blocking for the protons, and then we have the form factor and the M effective that are there for all the targets. So the form factor matters when the momentum transfer is large. So for dark matter masses that are heavy, so heavier than the target, let's say, so from 10 keV onwards. And the M effective is also relevant more or less in the same case, because you get, let's say, different reduced mass from an effective when the dark matter mass is very high. But it also matters in this case of this operator D1, it also matters at low mass, because the coefficient of the operator has the mass inside.
So D1, you have to remind me, what is that operator again?
It's basically scalar. I didn't include it. It's basically scalar. It's chi bar FF bar. Basically.
Okay. Scalar operator. Okay.
This is proportional to the mass. That's why you get the scaling also at low mass.
Okay, now that's good. That's interesting. Wait, okay, so let me just see. Okay, so for protons, the Pauli blocking is much larger the effect than for neutrons.
So in the case of protons, if you neglect the interactions, you get basically that the chemical potential of protons goes to zero. Towards and that means that basically you wouldn't have the polyblock. You neglect the polyblocking effect. While if you use the QNC equation of state, you get a non-zero chemical potential that allows you to have to consider polyblocking effect. A polyblocking effect has to be there. So it's an artifact of the free Fermi gas that you get.
Okay, thanks. Okay, I think we're at 5 o'clock. Let's finish the official part and thank